Lecture 1. Measuring reaction rate. Reaction rate tells us how fast a chemical reaction happens. More specifically, it measures how quickly reactants are used up or how quickly products are formed. If we measure a product, the concentration usually increases over time, so the rate can be written as rate equals change in product concentration divided by change in time. If we measure a reactant, the concentration usually decreases over time. Because that change is negative, we add a negative sign to keep the reaction rate positive. So for a reactant, rate equals negative change in reactant concentration divided by change in time. For example, if the concentration of A decreases from 2.5 molar to 0.6 molar in 20 seconds, the change is negative 1.9 molar. But reaction rate is reported as a positive value, so the rate is 0.095 molar per second. The key idea is simple. Products increase, reactants decrease, but reaction rate is always written as a positive number. Lecture 2. Instantaneous rate from graphs. Average rate tells us the rate over a time interval, but instantaneous rate tells us the rate at one exact moment. To find instantaneous rate from a graph, we draw a tangent line to the curve at that point. The slope of that tangent line gives the rate at that moment. For a product graph, the curve usually increases, so the slope is positive. That means rate equals gradient. For a reactant graph, the curve usually decreases, so the slope is negative. But reaction rate must be positive. So for a reactant graph, rate equals negative gradient. In this example, the tangent line at 20 seconds gives a change in Y of 24 milliliters and a change in X of 40 seconds. So the rate is 24 divided by 40, which equals 0.60 milliliters per second. A steeper tangent means a faster reaction. A flatter tangent means a slower reaction. Lecture 3. Stoichiometry and reaction rate. Reaction rate must describe the whole reaction, not just one substance. That means the rate has to account for the coefficients in the balanced equation. For a general reaction, AA plus BB gives CC plus DD. Reactants are disappearing, so their rates use a negative sign. Products are appearing, so their rates use a positive sign, but we also divide by the coefficients. That way, every substance gives the same overall reaction rate. For example, 2N2O5 gives 4NO2 plus O2. If N2O5 disappears at a rate of 5.0 times 10 to the negative 8 molar per second, then NO2 appears twice as fast because its coefficient is 4 compared to 2. So the rate of appearance of NO2 is 1.0 times 10 to the negative 7 molar per second. The coefficient ratio controls how fast each substance changes, but the reaction itself has one overall rate. Lecture 4. Factors affecting reaction rate. Several factors can change reaction rate. The first factor is concentration. When concentration is higher, there are more particles in the same volume. That means particles collide more often, so the reaction can happen faster. The second factor is temperature. At higher temperature, particles move faster and have more kinetic energy. More particles can overcome the activation energy barrier, so the rate increases. The third factor is surface area. A large solid chunk has fewer exposed particles, but powder has much more exposed surface area. That gives more places for collisions to happen. The fourth factor is a catalyst. A catalyst provides an alternative pathway with lower activation energy. This allows more particles to react successfully. So reaction rate increases when effective collisions become more frequent. That is the connection between all four factors. Lecture 5. Introduction to rate law. A rate law shows how the reaction rate depends on concentration. The general form is rate equals K times A to the power of meters times B to the power of N. Here, K is the rate constant. Meters and N are reaction orders. The overall order is meters plus N. But these exponents are not usually taken from the balanced equation. They must be determined experimentally. For example, if doubling the concentration of A doubles the rate, the reaction is first order in A. If doubling the concentration of B makes the rate 4 times larger, the reaction is second order in B. The important warning is this: do not assume the exponents from the overall balanced equation. The exponents match coefficients only for elementary reactions. For most reactions, the rate law comes from experimental data. Lecture 6. Concentration time graphs. Concentration time graphs show how concentration changes as a reaction proceeds. For reactants, concentration usually decreases over time. For products, concentration usually increases over time. At the beginning, the curve is often steep. That means the reaction is fast. As reactants are used up, collisions become less frequent, so the curve becomes flatter and the rate slows down. There are two ways to measure rate from the graph. Average rate uses 2 points. It measures the slope of the second line between those points. Instantaneous rate uses 1 point. It measures the slope of the tangent line at that point. For products, the slope is positive, so rate equals the slope. For reactants, the slope is negative, so rate equals negative slope. The shape of the curve tells us how the reaction rate changes over time. Lecture 7. Reaction order, K, and half-life. Reaction order affects the rate law, the units of K, the linear graph, and the half-life pattern. For a zero-order reaction, the rate law is rate equals K. The rate does not depend on the concentration of A. The linear plot is A versus time. The units of K are molar per second. For zero order, half-life decreases as concentration falls. For a first order reaction, the rate law is rate equals K times A. The linear plot is natural log of A versus time. The units of K are per second. The half-life is constant and equals natural log of 2 divided by K. For a second order reaction, the rate law is rate equals K times A squared. The linear plot is 1 over A versus time. The units of K are inverse molar per second. For second order, half-life increases as concentration falls. So each reaction order has its own graph, its own units, and its own half-life behavior. Lecture 8. Catalysts and reaction rate. A catalyst increases reaction rate without being used up overall. It works by providing an alternative reaction pathway with lower activation energy. On an energy profile, the catalyzed pathway has a lower peak. That means more particles have enough energy to react, so the reaction becomes faster. But a catalyst does not change the reactants or products. It does not change the overall enthalpy change, delta H. It also does not change the equilibrium position. If a reversible reaction is involved, the catalyst speeds up both the forward and reverse reactions. So equilibrium is reached faster, but the final equilibrium mixture stays the same. Enzymes are biological catalysts. Metal catalysts are also used in industry, for example in chemical production, petroleum refining, and emission control. The key idea is this: a catalyst lowers activation energy, increases reaction rate, but does not change delta H or the equilibrium position. Lecture 9. Elementary reactions and overall equations. Most reactions do not happen all at once. A balanced equation shows what we start with and what we end with, but it does not show what happens in between. For example, the overall reaction is CO plus NO2 gives CO2 plus NO. This equation tells us the reactants and products, but it does not tell us the actual path the molecules take. That path is called a reaction mechanism. A reaction mechanism is a set of elementary reactions. Each elementary reaction is one small molecular event. For this reaction, one possible mechanism has 2 steps. First, NO2 reacts with another NO2 to form NO3 and NO. Then, NO3 reacts with CO to form CO2 and NO2. When we add these 2 elementary steps together, anything that appears on both sides cancels out. NO3 is formed in the first step and used up in the second step. So NO3 is an intermediate. It is important in the mechanism, but it does not appear in the overall equation. The key idea is simple. The elementary steps must add up to the overall reaction. Lecture 10. Molecularity of elementary reactions. Molecularity tells us how many reactant particles collide in one elementary step. This only applies to elementary reactions. It does not apply to the overall reaction unless the reaction happens in just one step. An unimolecular step has one reactant particle, for example, a Gibbs products. Because only A is involved, the rate law is rate equals K times A. A bimolecular step has 2 reactant particles. For example, A plus B gives products. The rate law is rate equals K times A times B. A termolecular step has 3 reactant particles. For example, A plus B plus C gives products. But termolecular steps are rare because it is unlikely for three particles to collide at the same time with the correct energy and orientation. Now consider this example. CH3 Ber plus OH minus gives CH3OH plus Ber minus. The overall equation does not tell us the molecularity. We must look at the elementary steps. Step 1 has CH3, Ber and OH minus reacting together. That step is bimolecular. Step 2 has one particle breaking apart. That step is unimolecular. So molecularity describes each elementary step, not the overall reaction. Lecture 11. Collision model. Molecules must collide to react, but not every collision produces products. For a reaction to happen, the collision must satisfy two conditions. First, the particles need enough energy. This minimum energy is called activation energy. Second, the particles must collide with the correct orientation. If particles collide with too little energy, they bounce away. No reaction occurs. If particles collide with enough energy, but in the wrong orientation, they still may not react. The important bonds may not line up correctly. An effective collision happens when the particles have enough energy and the correct orientation. Then bonds can break, new bonds can form, and products are made. Reaction rate increases when effective collisions become more frequent. That is why concentration, temperature, and surface area matter. Higher concentration means more particles in the same volume, so collisions happen more often. Higher temperature makes particles move faster, and more particles have enough energy to pass the activation energy barrier. Greater surface area exposes more particles to collisions. So the collision model explains reaction rate at the molecular level. Lecture 12. Reaction energy profiles. An energy profile shows how potential energy changes as a reaction happens. The vertical axis is potential energy. The horizontal axis is reaction progress. The activation energy, EA, is the minimum energy needed for the reaction to occur. On the graph, the peak of the curve is the transition state. This is also called the activated complex. At this point, old bonds are partially breaking and new bonds are partially forming. The energy difference between products and reactants is called delta H. If the products are lower in energy than the reactants, delta H is negative. That means the reaction is exothermic. Energy is released to the surroundings. Combustion and neutralization are common examples. If the products are higher in energy than the reactants, delta H is positive. That means the reaction is endothermic. Energy is absorbed from the surroundings. Photosynthesis and thermal decomposition are common examples. So when reading an energy profile, always identify three things: the activation energy, the transition state, and the overall energy change, delta H. Lecture 13. The Arrhenius equation. The Arrhenius equation connects temperature, activation energy, and the rate constant. The equation is K equals A times E to the power of negative EA over RT. Here, K is the rate constant. A is the frequency factor. It represents how often particles collide and how often they collide with the correct orientation. EA is the activation energy. R is the universal gas constant. T is the absolute temperature in Kelvin. The important idea is that temperature changes the value of K. When temperature increases, more molecules have enough energy to overcome the activation energy barrier. On the Maxwell-Boltzmann distribution, this means the area to the right of EA becomes larger. That area represents the fraction of molecules with enough energy to react. At lower temperature, only a small fraction of molecules have energy greater than EA. At higher temperature, a much larger fraction does. So higher temperature usually means a larger rate constant and a faster reaction. Higher activation energy has the opposite effect. If EA is larger, fewer molecules can overcome the barrier, so the reaction is slower. The key idea is this: temperature changes reaction rate because it changes how many molecules have enough energy to react. Lecture 14. Reaction mechanisms. A reaction mechanism describes how a reaction occurs at the molecular level. It is a sequence of elementary steps. The same overall reaction can sometimes happen by different mechanisms under different conditions. For example, consider the reaction between CO and NO2. At high temperature, the reaction can be shown as one elementary step. CO plus NO2 gives CO2 plus NO. But at lower temperature, the same overall reaction can occur through two steps. Step 1, NO2 plus NO2 gives NO3 plus NO. Step 2. NO3 plus CO gives CO2 plus NO2. When these two steps are added, the final overall reaction is still CO plus NO2 gives CO2 plus NO. NO3 is an intermediate. It is formed in one step and consumed in a later step. A proposed mechanism must satisfy important conditions. The steps must add up to the overall reaction. The steps must be chemically reasonable. And the mechanism must match the experimental rate law. So mechanisms are not just random guesses. They are proposed from evidence. Lecture 15. Intermediates versus transition states. Intermediates and transition states are not the same thing. An intermediate is produced in one elementary step and consumed in a later step. It appears in the mechanism, but not in the overall equation. On a multi-step energy profile, an intermediate is found in a valley. That valley is a local minimum. It means the intermediate is more stable than the transition states around it. Some intermediates can sometimes be detected. For example, NO3 can act as an intermediate in the reaction between CO and NO2. A transition state is different. A transition state exists at the top of an energy barrier. It is the highest energy arrangement during a step. It is extremely unstable and cannot be isolated. On the energy profile, transition states are the peaks. Intermediates are the valleys. So if you see a multi-step energy diagram, count the peaks to find transition states and count the valleys between peaks to find intermediates. Lecture 16. Mechanism and rate law. The rate law for a reaction is connected to the reaction mechanism. In a multi-step mechanism, the slowest step is called the rate determining step. This step controls the overall reaction rate. Think of it like traffic. Even if several roads are fast, one slow bottleneck controls how quickly everything moves. Here is a sample mechanism. Step 1 is slow, A plus B gives C. Step 2 is fast, C plus D gives E. The overall reaction is A plus B plus D gives E. Because step 1 is the slow step, the rate law comes from step 1. For an elementary step, the exponents in the rate law match the coefficients of the reactants in that step. So for A plus B gives C, the rate law is rate equals K times A times B. That means the rate depends on the concentration of A and the concentration of B. Be careful. Do not write the rate law directly from the overall equation unless the overall equation represents one elementary step. For most reactions, the rate law must come from experimental data or from the rate determining elementary step. Lecture 17. Pre-equilibrium approximation. Sometimes the slow step contains an intermediate. That creates a problem. The final rate law should usually be written using reactants from the overall reaction, not an intermediate. The pre-equilibrium approximation helps solve this. Imagine a mechanism with two steps. Step 1 is a fast equilibrium. A plus B reversibly forms I. Step 2 is slow. I plus C gives products. Because step 2 is slow, we first write the rate law from step 2. Rate equals K2 times I times C. But I is an intermediate, so we want to replace it. Since step 1 is a fast equilibrium, we can write an equilibrium expression. K equals I divided by A times B. Rearranging gives I equals K times A times B. Now substitute this into the slow step rate law. Rate equals K2 times I times C. Replace I with K times A times B. So the final rate law becomes rate equals K2 times K times A times B times C. The key idea is this. When the first step is a fast equilibrium, use that equilibrium to express the intermediate concentration, then substitute it into the slow step rate law. Lecture 18. Multi-step reaction energy profile. A multi-step energy profile shows every elementary step in a mechanism. Each peak represents a transition state. Each valley between peaks represents an intermediate. In this diagram, there are 3 peaks. That means the reaction has 3 elementary steps. There are also 2 valleys between the peaks. That means the reaction has 2 intermediates. Each step has its own activation energy. For step 1, EA1 is the energy difference between the reactants and transition state 1. For step 2, EA2 is the energy difference between intermediate 1 and transition state 2. For step 3, EA3 is the energy difference between intermediate 2 and transition state 3. The highest activation energy barrier is usually the rate determining step. In this diagram, transition state 3 has the highest barrier. So step 3 is the rate determining step. The diagram also shows delta H for the overall reaction. Delta H is the energy difference between the reactants and the products. If the products are lower than the reactants, delta H is negative and the overall reaction is exothermic. So to read a multi-step energy profile, follow this pattern. Peaks are transition states, valleys are intermediates. The highest peak usually controls the rate. And the difference between reactants and products gives the overall energy change.